All right, welcome back everyone to lecture 8. Today we're going to talk about attention and transformers, and I think this is a really fun one. So as a quick recap, last time we were talking about recurrent neural networks, and recurrent neural networks were this new kind of neural network architecture meant for processing sequences. And in particular, we saw how neural networks, by processing sequences, let us attack a whole new different kinds of problems than we could with convolutional networks before. So in particular, usually we had been thinking about these one-to-one problems, where you input one thing, like an image, and then output one thing, like a classification for what's in that image. But once you have the ability to move beyond images and move towards sequences of data, it let us tackle a lot of new kinds of problems, like one-to-many problems, image captioning. Maybe we want to input an image, output a textual description of that image, which is going to be a sequence of words. Maybe many-to-one, where we do input a sequence of frames and output a classification for those frames, and a bunch of other problems along this vein. So now we're seeing that moving into these more sophisticated neural network architectures, both is sort of more interesting architecturally, but also lets us tackle new problems than we could with kind of more traditional feed-forward neural networks. So today we're going to build on that and talk about two new things in today's lecture. The first thing is going to be attention, which is going to be a brand new neural network primitive that fundamentally operates on sets of vectors. And then the second thing we're going to talk about is the transformer. And the transformer is a different neural network architecture that has self-attention at its core. And the spoiler alert is that transformers are basically the architecture that we use for almost all problems in deep learning today. So any of the largest applications that you're seeing out there in the wild today, whether it's classifying images, generating text, classifying text, working with audio, basically any kind of large neural network today that is large, state-of-the-art, trained on a lot of data, deployed by a big company, almost all of them are going to be transformers today. So that's really exciting that we get to get you up to speed on the latest and greatest architectures that people are using now. But even though transformers are this sort of state-of-the-art architecture that everyone is using for everything today, they have a relatively long history. And they initially, it's kind of interesting watching these fields develop, because looking back on it, when the moment that transformers came out, it feels like it ought to have been this big moment, this big thing when there was a big sea change, this new architecture, this new thing. But it actually didn't feel that way. Because even though there was one moment where the transformer architecture was born, these ideas around self-attention, around using attention in various ways, those had actually been around in the field for several years at that time. And in particular, these ideas around attention, self-attention, they actually developed out of recurrent neural networks. So we're going to start there to talk about and motivate these problems. So this is going to be a little bit mirroring the historical development of these ideas. So for that reason, we're actually going to, in order to introduce transformers, we're actually going to roll back and recap a little bit about this idea of recurrent neural networks that we saw in the last lecture. So as a motivating problem, let's think about this sequence-to-sequence problem of translation. So we want to input one sequence, which is going to be a sequence of words in English. Then we want to output another sequence, which is going to be a sequence of words in a different language, Italian, right? And and we can't make assumptions that there's any correspondence between those words, right? The number of words in the English sentence might be different from the number of words in the Italian sentence, and the order of those words might be totally different. So this is a perfect application of the kind of sequence processing algorithms sequence processing architectures that we saw in recurrent neural networks. And indeed, this idea of processing these sequence-to-sequence problems with recurrent neural networks, this goes all the way back to 2014, even a bit earlier than that. But people have been processing sequences with recurrent neural networks for more than a decade at this point. So the basic architecture for processing sequence-to-sequence problems with recurrent neural networks is that typically you'll start with one encoder. Your encoder is a recurrent neural network. The recurrent neural network, recall, is this function that gets applied recursively on two inputs. One is your xt, your input at the current time step, and the other is your ht-1, which is your hidden state at the previous time step. And your recurrent neural network unit will then spit out a next hidden state at the next time step. And then we can apply that same recurrent neural network unit over in time to process a sequence of potentially variable length. So in this case, we're using a recurrent neural network encoder that inputs the input sequence in English. Input sequence, you got to use relatively short sentences to fit on slides and still have all the boxes show up. So we're using a kind of short, silly sentence. We see the sky. And this, each word in that sentence gets processed via one tick of the recurrent neural network. And then the idea of this encoder recurrent neural network is it wants to process all of the words in the input sequence and somehow summarize the content of that input sentence so that we can translate it into into our output target language. So the more concrete way that this happens is that after processing all the words in the input sequence, we're going to summarize the entire content of that input sequence into a single vector called the context vector. And there's a couple different ways that people would typically do these in recurrent neural networks. I don't think the details are too interesting. So you can just think that context vector is basically the last hidden state of the encoder recurrent neural network. And now the idea is that because, because of the recurrent structure of our recurrent neural networks, the last hidden state sort of incorporates information of the entire input sequence. So we can think of that last hidden state as summarizing or encoding all of the information in the entire input sequence. So then that is one vector that is going to kind of summarize that entire input sequence to do whatever we want with it. And in this case, what we want to do with it is translate that input sequence into an output sequence in a different language. So to do that, we're going to use a second recurrent neural network called the decoder, which usually has the same architecture, but potentially a different weight matrix, different set of learned parameters. And this decoder, GU, is going to be a different recurrent neural network with different learnable weights U, but has the same basic idea. Now, our recurrent neural network unit is going to take 3 inputs at every time step. It's going to take YT-1, which is the token in the output sequence at the previous time step. It's going to take ST-1, which is the previous hidden state in the output sequence, and C, which is that context vector summarizing the entire input sequence. And then we kind of unroll that output sequence, just as we saw in the last lecture, and produce words one at a time in the output sequence. And I don't speak Italian, so I'm not going to try to pronounce these, but there's some Italian words on the screen that you can see. And I'm assuming that indeed translates to "we see the sky." Hopefully that's correct, right? But the idea is we're going to tick this recurrent neural network one tick at a time. It's going to output words one at a time. And this is basically a summary of what we saw last lecture. So this should basically not be too surprising in light of the previous lecture. But there's a potential problem here, right? And there's a communication bottleneck here between the input sequence and the output sequence, right? The only way in which the input sequence is communicating with the output sequence is via that context vector C. And that C is going to be a fixed length vector, right? Because the size of that vector is fixed when we set the size of our recurrent neural network. And maybe that's fine, right? So C might be a fixed length vector of 128 floats, 1024 floats. But the size of that input vector is not going to change as our input and output sequence sizes grow or shrink. And that's a potential problem, right? So if we're doing short sequences, like "we see the sky," maybe it seems pretty plausible that we can summarize everything we need to know about that sequence in that fixed vector of 1024 floats. But what if we're not trying to translate 4 words? What if we're trying to translate a whole paragraph or a whole book or an entire corpus of data? Then in that case, we're going to run into a bottleneck where at some point, as we scale that input sequence, it's just not going to be sensible to ask the network to summarize the entire input sequence into a single fixed length vector. So that's going to be a problem. So the solution here is actually, let's not bottleneck the network through one fixed length vector. Instead, let's change the architecture of our recurrent neural network. Intuitively, what we want to do is not force a bottleneck in a fixed length vector between the input and the output. Instead, as we process the output sequence, we're going to give the model the ability to look back at the input sequence. And now every time it produces an output vector, we want to give the network the opportunity to look back at the entire input sequence. And if we do this, there's going to be no bottleneck. It will scale to much longer sequences, and hopefully the model architecture will work much better. So that's the motivating idea that led to attention and transformers and all this great stuff that we see today. It all came, one way of telling the story is that it all came from trying to solve this bottleneck problem in recurrent neural networks. So let's see how we can actually implement this intuition and endow our recurrent neural network with the ability to look back at the input sequence on every time step. So here we're going to, start with the same thing. Our encoder neural network is going to remain the same, no changes there. We still need to set some initial hidden state for the output sequence. And so we need to set some initial decoder state S0 in some way. But now, once we have that decoder hidden state, what we're going to do is look back at the input sequence. So the way that we're going to do that is by computing some alignment scores by comparing that that basically compute a scalar value for each step in the input sequence that says how much does that initial decoder state S0, how much does that decoder state match each token of the input sequence. So in this case, there were 4 tokens in the input sequence. So we want to compute 4 alignment scores, each of which is just a single number that says what is the similarity between the input sequence, the token of the input sequence, and this initial decoder state S0. Now, there's a lot of ways that we could implement alignment scores, but a simple way is just use a simple linear layer that we're calling F sub ATT. And so that linear layer is going to concatenate the decoder hidden state S with one of the encoder hidden states H, concatenate those 2 into a vector, and then apply a linear transform that squashes that down into a scalar. And that's just a linear operator that can be put into a computational graph and learned jointly via gradient descent, just in the way that we learn all other parameters of a network. So now at this point, we've got sort of this scalar alignment score for each step in the input sequence. And now we want to apply a softmax function, right? These scalar alignment scores are totally unbounded. They're arbitrary real values from minus infinity to infinity. We want to put some structure on this to prevent things from blowing up. So one way that we do this is apply a softmax function. So we've got 4 scalar values telling us the alignment of that decoder hidden state, with each of the encoder hidden states. Now we apply a softmax over those 4 values to give us a distribution over those four values. So remember, the softmax function that we saw a few lectures ago is going to take a vector of arbitrary scores and convert it into a probability distribution, which means it'll have the property that each entry in the output softmax probabilities will be between 0 and 1, and they will sum to 1. So we can think of, whenever we run a vector through a softmax, we can think of the thing we get out as a probability distribution, or rather a discrete probability distribution over those input scores. So at this point, after we take those alignment scores and run them through a softmax, what we've essentially done is predicted a distribution over the input tokens, given that decoder hidden state. So now what we want to do is take that distribution over the input tokens and use them to compute a vector, summarizing the information in the encoder. So the way that we do that is we take our attention scores, which recall are these numbers A11, A12, A13, A14. They're all between 0 and 1. They sum to 1. We're going to take a linear combination now of the encoder hidden states, H1, H2, H3, H4, and take a linear combination of those encoder hidden states weighted by our attention scores. And this will give us a context vector that we're calling C1 here in purple, which is going to summarize the information in the encoder sequence in some way that's modulated by those attention weights. And now at this point, right, so then this C1 is basically some linear combination of the input encoder states H1 to H4. Things look basically the same as they did in the non-attention case. So we have our context vector. We concatenate it with our first token of the output sequence, Y0, pass that to our recurrent unit to get our next hidden state of the decoder recurrent neural network, as well as the first output token from the decoder recurrent neural network. So basically, the structure of that decoder RNN did not really change. All we did is, we computed the context vector in a different way using this attention linear combination mechanism. But now, crucially, right, so the intuition here is that this context vector basically attends or looks at different parts of the input sequence that is modulated by whatever the output RNN wants to look at this moment in time. So for example, part of the input, part of the input sequence has this token, these 2 words we see. So then in trying to produce that one word in Italian that corresponds to we see, the network probably wants to go back and look at those 2 words in the input sequence in order to know what output word to produce. So we might expect that intuitively when trying to produce the word vendiamo, then the network will want to look back at the words we see and put higher attention weights on those. And it doesn't really care about the sky because those 2 words are not necessary for producing that vendiamo output. And that's the kind of intuition. We're giving the network the ability to look back at the relevant parts of the input sequence for the word that it's trying to predict at this moment in time. And the other thing to keep in mind is that this is all differentiable. we don't need to supervise the network. We don't need to tell it which words in the input sequence were required for each word in the output. Instead, this is just a big computational graph composed of differentiable operations. All of this can be learned end to end via gradient descent. So at the end of the day, we're still going to have this, cross-entropy softmax loss where the network is trying to predict the tokens of the output sequence. And in the process of trying to predict the right tokens in the output sequence, it's going to learn for itself how to attend to different parts of the input sequence. So that's really critical, right? If we had to go in and supervise and tell the network the alignment between the two, it would be very difficult to get training data for this kind of thing. The question is, how do we initialize the decoder? We're actually using the word, you gotta be careful, we're using the word initialize a little bit overloaded here. So one question is the decoder is itself a neural network that has weights. When we start training that network, we need to initialize those weights in some way. So then we'll typically initialize the weights of the decoder randomly and then optimize them via gradient descent, just as we do with any other neural network weights. But there's a second notion of initialize, which is that when the network is processing a sequence, whatever its current value of the weights are, we need some way to set that initial hidden state at the time we start processing an output sequence. And in that case, we need some rule or some way to set that initial hidden state of the decoder output sequence. There's a couple different mechanisms for this. Sometimes you might initialize it as the last hidden state of the encoder is one thing you'll sometimes do. You might have a linear transform that has some learned projection from the last decoder state to the first, from the last encoder state to the first decoder state. Or sometimes people will even initialize the first hidden state of the decoder to be all zeros. Any of those will work as long as you train the network to expect that kind of input. So the question is, negations and XORs, would this cause a problem? Maybe. This is a hard problem, but then you need a lot of data, a lot of flops to try to hope the network can disentangle this. But basically, your recurrent unit takes three things as input. In the decoder, right? It takes the previous hidden state, the previous decoder hidden state. It takes the current context vector, and it takes the current token in the output sequence. And then from that, we produce the next hidden state. And then from the next hidden state, then we go and predict the output token. So that's actually the same setup as in the non-attention case. I guess there's an implicit connection there's a connection from S0 to S1 that we're not drawing. So there should have been another arrow from S0 to S1. I think I just dropped the S0 arrow, so sorry about that. Well, we're basically letting the network decide for itself to look back at any part of the input sequence that it thinks might be relevant for the task at hand. But the reason why we think that this mechanism is plausible and might be helpful for the network is because we know that, in a language task, there often is some kind of correspondence between words in the output and words in the input. And we want to let the network kind of look back and pick out which are the relevant bits of the input for producing this bit of the output. But again, we're not directly supervising it. We're not telling it how to use these attention scores. But the intuition is that we think that's a plausible thing that it might choose to do given this mechanism. Okay, so that's sort of like one tick of the output. And now basically we do it again. We do this whole process again for every time we tick the decoder RNN. Right? Remember the problem we were trying to solve is that previously the decoder was bottlenecking through a single vector. Now we're going to compute, instead of bottlenecking through a single vector, we're going to repeat this whole process again and compute a new context vector for the second time step of the decoder and let it go back and look at the whole input sequence yet again. So now, basically, given our S1, which is our computed first hidden state in the decoder, we're going to go back, take S1, go back and compute comparison and use our attention mechanism to compute similarity scores between S1 and all of the hidden states in the encoder. That will compute our similarity scores using that exact same FATT, that same linear projection that we used at the first time step. Compute these alignment scores. Again, cram them through softmax to get a new distribution over the input sequence for the second decoder time step. And now compute a new linear combination of the encoder hidden states, now weighted by this new distribution that we computed at the second time step. And this will basically give us a new context vector, C2, that now is a different summarization of the input sequence that's now computed as a new linear combination of the input encoder hidden states. And then the whole thing kind of iterates, right? We have a new context vector. We use that to run another tick of our decoder RNN unit that will now does include that mysterious missing arrow that wasn't there on the previous time step. So then given our new context vector, given the next token of the output sequence, and given the S1 hidden state of the decoder, we compute a new decoder state S2, and then from that compute another token of the output sequence. And again, remember, in this case, it's producing ill, which maybe is the, according to the slide. I hope that's true. And then, in this case, there's maybe a one-to-one correspondence between the word the network is trying to produce for this sequence and one of the words in the output, and one of the words in the input. So we might expect that the network should put relatively high attention weight on just one of the words in the input sequence and relatively low attention weight on all the other words in the input sequence. But again, we don't supervise this. The network is deciding for itself how to make use of this mechanism, all driven by gradient descent on our training task. And this whole thing is we're just gonna repeat that whole process for every tick of the decoder RNN. So now this basically solved our problem, right? We are no longer bottlenecking the input sequence through a single fixed length vector. Instead, we have this new mechanism where at every time step of the decoder, the network looks back at the entire input sequence, re-summarizes the input sequence to generate a new context vector on the fly for this one time step of the decoder, and then uses that to produce the outputs. So this is a pretty cool mechanism. And this is called attention, because the network is attending or looking at different parts of the input sequence at every moment in its output. So we talked about these attention weights, and we said that they were driven, the network was learning for itself how to set these attention weights based on its training data, based on its training task. And another really cool thing about attention is that it also gives us a way to introspect and see what the network is looking at as it's trying to solve this problem. So we never told it how what the alignment was between the input sequence and the output sequence, but by looking at the attention weights that the network predicts when trying to solve this task, we get a sense of what the network was looking at while trying to solve the problem. So that gives us a way to interpret the processing of the neural network in some way. And so one thing that we can do is then go and look at, in the process of producing processing a particular sequence, what were the attention weights that the network predicted when trying to do this task? And we can visualize these in a two-dimensional grid. So here we're looking at an example of English to French translation, and across the top we have our input sequence. The agreement on the European Economic Area was signed in August 1992. And then running down the rows is the output sequence, which is in French, which I will not attempt to pronounce. But you can see that, basically through this attention mechanism, remember the way this attention mechanism worked is that each time the network produced one of these words in the output sequence, it predicted a probability distribution over the entire input sequence. So we visualize that in that first row. So if you look at the first row of this matrix, we're visualizing that predicted probability distribution over the entire input English sentence. And we see that when trying to predict that first word le of the French sentence, then it puts a lot of probability mass on the English word the, and basically no probability mass on any of the other words. Then when predicting the second word of the output sequence, remember it goes back and predicts a new distribution over the entire input sequence, and that's going to be the second row in this matrix. So you can see that accord, it puts a lot of probability mass on agreement and then no probability mass anywhere else. So then that gives us some sense that the network actually kind of did figure out the alignment between the input words and the output words when doing this translation task. And there's some interesting patterns here that kind of pop up. When we see diagonal structures in this attention matrix, that means that there was a one-to-one correspondence between words in order between the input sequence and the output sequence. So in particular, we see that the agreement on the first four words of the input sequence, correspond to this diagonal structure in the attention matrix. So that means that the network has decided for itself that these first four words of the input sequence sort of align or match up or correspond to the first four words of the input sequence. And the same thing for the last several words. So again, we see this diagonal structure at the end of the sequence, which means that August 1992 or in August 1992 corresponds to these last couple words in the French sequence. And again, there's this one-to-one correspondence between words in the output and words in the input. But we see some other interesting stuff in the middle here. So in the middle, we see European Economic Area, but in the French, we see words that look kind of like those in a slightly different order. Good question. How does it figure out the grammar? That's the mystery of deep learning. But basically, we didn't tell the network anything about grammar. We told the network, we supervised it with a lot of input-output pairs. We told it, here's an input sequence in English, here's an output sequence in French, here's a mechanism for processing this, and learn via gradient descent to like set the weights of this architecture in order to produce this output from this input. We'd never told it anything about grammar. But it kind of, because we as human designers have this intuition that maybe it makes sense that there ought to be some correspondence between some of the words. So we bake in a mechanism that we think as the human designers might be helpful for solving this problem. And the network figures out for itself in the process of doing the end-to-end task how to make use of that mechanism to solve the problem we set for it. And it's pretty amazing that it works. Right, but in this case, it kind of figured out some of the grammar for itself. So it sees that, we see this non-diagonal, sort of backward diagonal in the attention matrix here, and that means that the network figured out for itself this like different word order between words in English and words in French. Or in the middle, you see there's a little like 2x2 grid, kind of here. And that kind of corresponds to a situation where there might not have been a one-to-one correspondence between the English words and the French words. There might have been two French words that corresponded to two English words, and they didn't perfectly disentangle perfectly. The network just all figures out this for itself over the process of training on a lot of data and putting a lot of compute through this. And that's pretty cool. Okay. So there's actually, and this actually was the initial usage of attention in machine learning. It actually came from these machine translation problems. So this was from a paper back in 2015, neural machine translation by jointly alerting to align and translate. And this paper actually just won the runner-up test of time award at iClear 2025. So that's pretty cool. A nice, this has been a really impactful paper over time. But it turns out that there's actually a more general idea here and a more general operator hiding here. We approach this problem from the perspective of trying to fix our recurrent neural networks. But it turns out the mechanism that we used to fix the recurrent neural networks actually is something general and interesting and really powerful in its own right. So now we want to try to pull out this idea of attention and divorce the idea of attention from the recurrent neural networks. And it turns out that attention will be a very useful and powerful computational primitive for neural networks in its own right. Even if then we can cut away the recurrent neural network part and just be left with attention as the core primitive in our architecture. And that's kind of where we're going towards. So now what we want to do is take this idea of attention as we saw it in recurrent neural networks and try to generalize it and try to carve out this independent operator that can be used on its own. So let's think about what this attention mechanism was doing. Basically, what this attention mechanism did is there were a bunch of query vectors. These are, well, maybe it makes sense to talk about these in the other order. So there's data vectors, which are like data that we want to summarize. These are the encoder states of the encoder RNN. So we have this input sequence, and we've summarized that into a sequence of vectors. And the sequence of vectors is sort of data that we think is relevant for the problem that we're trying to solve. And now, in the process of trying to make use of that data, we want to produce a bunch of outputs. And for each output, we have a query vector. A query vector is a vector that we're trying to use to solve to produce some piece of output. And in this case, the query vectors are the hidden states of the decoder RNN. And we have this property that for each query vector, we want to go back, look at the data vectors, and summarize the information in the data vectors into a context vector for each. Well, okay, from the purpose of attention, this gets a little bit weird. So the output of the attention operator are the context vectors that we just talked about for the RNN. So if we're thinking about just what does that attention operator do, the output of the attention operator were the context vectors that we feed into the RNN. So then what is the attention operator doing? The attention operator is taking a query vector, going back to the input data vectors, summarizing the data vectors in some new way to produce an output vector. And that's what the attention operator is doing. Does that kind of make sense as a generalization of this attention mechanism that we just saw? Yeah. I'll repeat it again because it's tricky. There's a lot of stuff flying around here, a lot of boxes, and we're changing the words that we're using to define the boxes. So I get it. There's a lot happening. So what the attention operator is doing is there's a bunch of data vectors, which are the encoder hidden states. Then we have a bunch of query vectors, which are the things we're trying to produce output for. Now, in the process of processing a query vector, we're going to go back to the data vectors, summarize the data vectors in a new custom way for each query vector, and that will produce an output vector, which is the context to be fed into the next tick of the RNN, right? So our query vectors are these guys in green. For each query vector, we go back to the data vectors, summarize the data vectors, and then produce a new output vector, which is one of the contexts that we then feed into the rest of the network. So, this is kind of tricky because we're trying to like go into this architecture and like carefully cut out the attention part and cut it out from the RNN. So then we're going to try to like walk through this again from the perspective of just the attention operator. So from the perspective of just the attention operator, we're going to start with just one query vector at first, which is, one of the states in our RNN. We also have a bunch of data vectors, which are the encoder hidden states in the RNN. Now, the computation that we want to perform is first compute similarities between that query vector and all of the data vectors. This is the exact same thing that we just saw, just sort of written in a different way. So we use this FATT function to compute these similarity scores to compute similarities between each data vector and our one query vector. Then once we have those similarities, we're going to squash them through a softmax to get attention weights. And this will be a distribution over the data vectors that has been computed on the fly for this one query vector. Then we want to do is produce an output vector. This output vector is a linear combination of our data vectors, where those linear combination weights are the attention scores that we just computed. So this is the output of the attention layer. And then in the context of the larger RNN that we saw, the output of the attention layer or the attention operator will become an input to the next tick of the decoder RNN. But we're trying to deprecate the RNN, so we don't want to talk about that. We just want to talk about the attention and focus on the computation happening inside the attention layer. So this is basically the operator that we saw in the RNN, right? We had this one, we did this process over and over again of taking a query vector, using it to compute similarity scores, getting attention weights, getting an output vector. Then we got a new query vector. Where did that query vector come from? Attention operator doesn't care. Get a new query vector, go back, summarize the data vectors, get a new output vector. And that's the core of the attention operator. So now let's try to generalize this and make it an even more powerful computational primitive. Yeah, so in principle, this FATT doesn't have to be, it could be any function. It could be any function of two vectors that outputs a scalar, in principle. But in practice, we're actually going to make it simpler in a couple slides. But in principle, yeah, you could just slot in any function that you wanted there. Okay, so the first generalization that we're going to do is actually the opposite of what you just suggested, and make that similarity function simpler. So we said in principle, it can be any function that takes two vectors and gives a similarity score. What's the simplest possible function that inputs two vectors and gives us a scalar similarity score? It's a dot product. So we want to try to make things simpler and also generalized at the same time. And it turns out that a dot product is good enough of a similarity score to be used for this purpose. So the first thing we're going to do is actually just only use dot products to compute similarity. But it turns out there's a slight problem with dot products. So, and this one's kind of subtle because there's a weird interaction between the dot product and the softmax. And that has to do with what happens when the dimension of those vectors scales up or down, right? So if you have the motivating example is that if you scale the dimension of that vector, say we had a constant vector of all ones of like dimension 10 versus a constant vector of all ones of dimension 100. Then as we go to the higher dimensional vector, then when we compute the sum inside that softmax, then we're going to be dividing by a larger number. So we'll end up with more squashed probability scores as we go to higher dimensional vectors. That can lead to vanishing gradients, as we just saw in the previous lecture, and prevent learning of this whole thing. So as kind of a slight hack to prevent that, and make this architecture more generalizably scalable up and down to different dimension vectors, what we're going to do is actually not use the pure dot product, but scale the dot product down by the square root of the dimension of those vectors that we're looking at. And this is just a way to prevent vanishing gradients and give nicer gradient flow through the softmax for a wider range of dimensions of vectors. And this turns out to be very important because as we make these networks bigger and bigger and bigger over time, we want to get higher dimensional vectors because that gives us more compute, more capacity. So we always want to think about how our architectures will scale as we make the parts of those architectures get bigger and bigger and bigger. So this scaled dot product is actually really important for preventing vanishing gradients here. Yeah, question was we're limited to data and query vectors of the same size, but we'll actually fix that. So our first generalization was to use actually scaled dot product similarity as our similarity measure. So now, if we go back and look at the shapes of these things, we have one query vector of dimension dq. We have data vectors of dimension nx by dq as well because it's a dot product they need to match. But But there's actually a next generalization that we're going to do is have multiple query vectors, right? Like maybe we don't want to process just one query vector at a time. We want to have the ability to process a whole set of query vectors all at once. And this kind of happens in the RNN. You know, we did end up with a bunch of query vectors. And it's useful for the attention operator to be able to process not one query vector at a time, but basically process a set of query vectors all in parallel and perform the exact same computation in parallel for a whole set of query vectors. So in this case, we've now generalized it to have n. So Q is now a matrix of shape NQ by DQ. So we have NQ query vectors. Each of those query vectors has dimension DQ. We have our data vectors is a matrix of size NX by DQ. And now, the computation changes a little bit because now when we compute these alignment scores, when we compute these similarities, basically we want to compute all pairs of similarities between all of the input data vectors and all of the input query vectors. And and each one of those similarities is a dot product. So, well, a scaled dot product. So, what's a very efficient and easy and natural way for us to compute dot products between two sets of input vectors? That turns out exactly to be a matrix multiply, right? Because remember, when you do a matrix multiply, each entry in the output matrix is the inner product of one of the columns of one of your matrices and the rows of your other matrix. And that's what, so then each entry in the output of a matrix multiply is exactly the dot product between the rows and the columns in the output. So this, by computing a matrix multiply between our query vectors Q and our data vectors X, and you need to get a transpose in there to make the rows and columns match up in the right way. This basically gives us, lets us compute all the similarities between all the data vectors and all the query vectors, all in one simple matrix multiply. Now we still need to compute these attention weights. Remember, the attention weights we want to compute for each query vector. We want to compute a distribution over the data vectors. Well, we already have these. Now our similarity scores are not just a single vector of scores. They're now a matrix of scores giving all the similarities. But we still want to compute a distribution over the data vectors for each query vector independently. So now we need to compute the softmax over just one of the axes of that matrix of similarity scores. So this is basically the exact same computation that we just saw. We're just doing it in parallel for a set of query vectors all at once. Now we need to compute the output vectors. And remember, the output vectors were going to be a weighted combination of the data vectors, where those weights are the values in the softmax. And it turns out that this is also something that matrix multiply does. Another way to think about matrix multiply is that when you take a matrix multiply of two matrices, a different way to view a matrix multiply is that it takes a linear combination of, oh man, am I going to get the rows and the columns in the right way? But I think you get the linear combination of the columns of one of your input matrices weighted by the values in the other input matrix. So this is another interpretation of matrix multiplication. So then if you kind of work through the indices and draw some little pictures for yourself to prove to yourself what's going on, it also turns out that, in order to compute, now what we want to do is compute many linear combinations of the data vectors, where each linear combination will be given by the probabilities in one of the rows of the attention matrix. So we can compute all of these all at once with another matrix multiply between the attention matrix A and the data vectors X. And again, you need to get the transposes in the right order to make this work out. But basically, this is the exact same operation that we just saw, but we're now doing it for a set of query vectors all at once. And it turns out that we can do it all at once with just a couple matrix multiplies. There's a next way that we'll generalize this is notice that in this equation, the data vectors X are actually entering in two different places in this computation. The first place that we're using the data vectors X is to compute similarities with the query vectors in this similarities computation. So in that notion, what we're trying to do is say, hey data vector, how much do you line up with each query vector as measured by an inner product? But then we're also using the data vectors again to compute the output vectors. So the output vectors are now a linear combination of the data vectors weighted by our attention weights. And it maybe seems a little bit weird to reuse the data vectors in those two different contexts. So now what we want to do is separate those two usages of the data vectors and let the network sort of figure out for itself two different ways to use the data vectors in those two contexts. So to do that, we'll introduce this idea of keys and queries. So now what we're going to do is, we had a set of data vectors, but what we're going to do is for each data vector, we're going to project each data vector into two vectors. One is a key vector, one is a value vector. And the idea of the key vectors are going to be compared with the query vectors to compute the alignment scores. And the value vectors are what we're going to compute linear combinations of in order to compute the output from the layer. And this also, so then the way that we implement this is we add two learnable weight matrices, the key matrix and the value matrix, which are going to be linear projections that project the project the data vectors into key vectors and value vectors. So now the data vectors are, we have n data vectors, each of dimension dx. So now the key matrix is a linear transformation that projects from dx into dq, right? Because we know that we're going to compare the key vectors with the query vectors, so they need to have the same dimension as the query vectors. So that will project so then applying matrix multiply of k equals xwk will project each data vector into a key vector of dimension dq. Then we'll separately have another weight matrix that projects from dx to dv, which is the dimension of the value vectors, which in principle could be different than the query vector dimension. And then we'll separately project each data vector into a value vector, again with a matrix multiply operator here. And the intuition here is that it's kind of like in a search engine, like you want to separate what you're looking for from the answer you want in response to that query, right? So like you go to Google or these days ChatGPT and you type in like, what is the best school in the world? That's your query. And then the value you get, that's the query that needs to be combined with the keys in the back end. But then the value, the data you want to get back from that query is actually different from the query you typed in, right? So we want to separate this idea of like, you put your query in, what is the best school in the world? That query needs to go match on all the different strings on the internet. And then the value you want to get back from that query is Stanford, which is a different value, which is different from the query that you put in. So that's kind of the intuition, another intuition between separating the keys and the queries and the values in this way. The query is what I'm looking for. The key is, in the back end, we have some record of all the data back there in the data vectors. But when we query, we want to match up against potentially just part of the data vector. And then the thing we want to get back from the data vector is the value. So we're separating the usage of the data vectors into those two different notions of keys and values. Then we can visualize this in a different way. So now we're finally throwing away the RNN and we're looking at attention just as an operator on its own. So we can step through this operation again. We've got our query vectors coming in. We've got our data vectors coming in. Now what we're going to do is from the data vectors, we're going to project each data vector into a key and a value. Then we're going to compare each key with each query to get our similarity scores. Right? So this is a matrix of scalars giving the similarities between each key and each query. Then once we have this matrix of similarity scores, we want to compute a distribution over the data vectors for each query. So that means we need to run softmax over this matrix of alignment scores, where we compute the softmax over each row. Then what we do is we want to reweight the value vectors by the attention scores in the softmax. Oh, actually, no, sorry. We want each column to be a distribution, right? Because we want for each query a distribution over the keys, which means we want softmax over the columns, right? Because we want it to be aligned to the columns. So then what we do is, we've got this query one. We've predicted this distribution over all of the keys from this computation. Then we're going to take a linear combination of the values weighted by these attention weights and compute a linear combination of the value vectors to produce our first output vector, y1. And then the same thing happens over here. Our second query got compared with all the keys. We computed a distribution over those alignment scores to get a distribution over the keys for the second query, which then get linearly combined. Then we use those to linearly combine the values to produce our output vector. So now this is the attention operator sort of standing on its own, divorced from the recurrent neural network. The question is, how do you divide the data vector into keys and values? The beautiful part is we don't have to say how. We just give the neural network the capacity to split it by itself by giving it this mechanism to project separately into keys and values, but we're not going to tell it how to do it. These are just going to be, the key matrix and the value matrix are just going to be learnable parameters of the model that will be learned via gradient descent along with everything else. So just as we did not tell it how to align the English and the French sentences, all of that was sort of learned via gradient descent. The model will learn for itself how to separately project into keys and values in a way that's sensible for the problem, that's helpful for the problem it's trying to solve. So that the keys and values, you might think of it as some kind of filter, right? So the data vector might have a lot of stuff in there, but for the task at hand, we might want to filter the data vector in various ways and only try to match our queries against part of it, and we only care about retrieving information of a different part of it. So you could think of those as, filtering, the information in the data vector in two different ways. Okay, so this is basically our attention operator. And now, there's no RNN here. This is just a neural network layer that you could have standing on its own, right? It receives two inputs, the query vectors and the data vectors. It has two weights of learnable parameters, which are the key matrix and the value matrix. It inputs two sequences of vectors, outputs a sequence of vectors. So this is a neural network layer in its own right that you could start to plug into your neural network architectures in various places. This is sometimes called a cross-attention layer, because it has two sets of inputs coming in, right? The idea is we have both data vectors and query vectors. They're potentially coming from two different sources. And this is sometimes useful, right? So that I have a set of queries. For each query, I want to go and summarize information from my data, which is potentially different or a different number or totally different from my query vectors. So this is sometimes called a cross-attention layer, because we're cross-attending between two different sets of things. But there's another version of this that happens, maybe even more commonly, is a self-attention layer. So here, what we're going to do is we only have one set of things. We only have one sequence of inputs. We have one set of vectors, one sequence of vectors that we're processing. So now we no longer have this separation between data vectors and query vectors. We just have one set of input vectors that we would like to process. So in a self-attention layer, we're going to have a set of input vectors, and we're going to produce a set of output vectors. So we want to input a set of vectors x, output a set of vectors y that are the same number as the input vectors. But now the mechanism of this is basically the same attention mechanism that we just saw. But now, rather than projecting, then we're still going to use this notion of filtering, but now, rather than projecting our data vectors into keys and queries, as we previously did, now what we're going to do is take each one of our input vectors and project it to three different things. From each of our input vectors, we're going to project it to a query, to a key, and to a value. And so the equations change just a little bit, but the picture over here doesn't actually change very much. For each of our input vectors, we separately project it to a query, to a key, and to a value. And now we have, the exact same computation. Now we've got queries, we've got keys, we've got values. From the perspective of everything happening up here, it's all the same. It just so happened that we computed the keys and the queries and the values all from different linear projections of those same input vectors. But all the computation is otherwise shared. Yeah, the question is what are D in and D out? How are they sized? So these are going to be architectural hyperparameters of the layer, right? Like just when we have a learnable linear layer in a model, a linear layer basically projects from a D in to a D out. Those are going to be architectural hyperparameters of the layer. Same thing with a self-attention layer. The D in and the D out are going to be architectural hyperparameters of the layer. And in principle, they could be different, right? There's enough flexibility in this architecture so that in principle, D in and D out could be different. Although I don't think I've almost ever seen that. In practice, they're almost always the same. So I've been a little bit extra general in the notation here. Okay, so I don't know that we necessarily need to walk through this. Oh, actually there is one important thing, right? So I said that we are separately projecting the inputs into queries, keys, and values. So that happens via 3 matrix multiplies with our 3 learnable weight matrices. Now we have 3 learnable weight matrices, one for keys, one for values, one for queries, and we separately project the input vectors x into keys, queries, and values. But in practice, we can actually typically compute just one matrix multiply all at once for those, because it's typically more efficient on hardware to do fewer large matrix multiplies than it is to do more smaller matrix multiplies. So a pretty common trick in practice is to sort of concatenate these 3 matrices along the dimensions and compute all of these keys, queries, and values for all the input vectors all at once with one big matrix multiply. If you've read transformers before, they sometimes separate between encoder and decoder transformers or encoder-decoder attention. So in that case, this would be the decoder only attention, if you've read transformer papers before, and which corresponds to the way that it's used in the decoder of the RNN in the initial example at the beginning of class. But this mechanism is actually just the most commonly used flavor of attention nowadays, is this sort of so-called decoder only attention. So we are quite divorcing ourselves away from the RNN now, right? So this flavor of it doesn't really make sense to be used in the RNN that we saw at the beginning of class, right? So we've basically been like doing a little bit of sleight of hand here, where we introduced this architecture for the purpose of RNN in this very concrete case of machine translation sequence to sequence. But we've now generalized it to become a totally different operator that can be used all on its own. And in this particular generalization into self-attention, it actually no longer can be used in that decoder in the RNN. But it's a very useful primitive that gets used in a lot of other places, it turns out. The question is, what's the benefit or difference between the self-attention versus the cross-attention? They would get used in different contexts. So in some situations, you naturally have two different kinds of data that you want to compare, which we saw, for example, in the machine translation setting. We have an input sentence, we have an output sentence. We believe that there's some natural structure in the problem, that there's two different sets of things that we want to compare. That also might happen in, say, image captioning, right? Say we have an input image, we want to produce an output sentence. There's two different kinds of things we want to compare. Pieces of the image and tokens in the words that we're generating. So for some problems, there's just this natural structure where you have two different kinds of things floating around. But for other problems, there aren't two kinds of things. There's just one thing. So say you're doing image classification, then there's only an image. We just want to process the image. So in that case, we just want to compare parts of the image with itself. And that's where you would use a self-attention layer. So they just get used for different kinds of problems. But crucially, we want to reuse basically the same machinery and the same computational primitives to be used in those different kinds of problems. And that's really beneficial. There's a couple interesting things about attention that I want to get through. So one is like, let's consider what happens if you permute the inputs, right? We had a set of input vectors. What happens if you shuffle them and process them in a different order? Now, actually, a lot of interesting stuff happens. So the keys, the queries, and the values will all end up the same, right? Because they are computed as linear projections of the input. So we'll end up getting the same keys, queries, and values. They'll just be in a different order, shuffled in the same way that the inputs were. And now, because our similarity scores were just dot products, we'll also end up with the same similarity scores, just again, kind of shuffled in accordance with the way we shuffled the input. Same thing with the softmax. Softmax doesn't actually care about the order of its inputs. So the softmax is now operating on the same vector, but shuffled. So each column of our attention weights will end up the same as they did before, just shuffled. And then same thing with linear combinations. So our outputs Y will actually still be the same outputs as we had before. They'll just all be shuffled. So that means that there's a really interesting structure here called permutation equivariance. Remember, we saw this a couple lectures ago with convolution. Now we see a different equivariance property of these self-attention layers, which is that if we shuffle the inputs, then we get the same outputs, just shuffled in the same way that the inputs were shuffled. And this kind of means, in this case, that self-attention doesn't actually care about the order of the inputs. If we change the order of the inputs, we'll get the same outputs, just shuffled in the same way. The computation of the layer does not depend on the order in which we present the inputs. So that means that we can think of self-attention actually not as operating on sequences of vectors. They happen to be packed into an ordered sequence of a matrix, but we really think of it instead as operating on an unordered set of vectors, because the outputs that we get don't actually depend on what order we packed those vectors into our input matrix. So we really think about this as a kind of different neural network primitive that fundamentally operates on sets of vectors rather than sequences of vectors. But this is sometimes a problem. Sometimes it is useful to tell the neural network what the order of the entries is. So as a quick fix to that, we'll sometimes concatenate an additional piece of data onto each of the input vectors called a positional embedding. That is basically some piece of data that tells the neural network, this one's at index 1, this one's at index 2, this one's at index 3, blah, 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 blah. And there's a bunch of different mechanisms for that. The question is it going to train to the same result? The training, I'm not really talking about the training here. I'm talking about if you fix the weight matrices and just consider the computation of the layer, then if I were to shuffle the inputs, then I receive the same outputs, but they'll be shuffled in the same way that the inputs were shuffled. So like the question of what vectors do I compute at the output does not depend on the vectors, on the order of the vectors in input. But the order of the vectors I get from the output does depend on the order that they were presented in the input. So there's another couple tricks we can do with self-attention, but I'll go through these a little bit faster. So sometimes, in a full self-attention layer, we allowed every piece of the input to look at every other piece of the input. But for some problems, we might want to impose some structure on this computation and say that certain pieces of the input are only allowed to look at certain other pieces of the input rather than everything being allowed to look at everything. And we can implement this via a notion called masked self-attention. So what we're going to do is after we compute these alignment scores E, we're going to go in and override the alignment scores with negative infinities in places where we want to block the attention. And now if you have a negative infinity in your alignment scores, then after you do a softmax, it's going to end up as a 0 if you walk through the softmax computation. So that means that if there's a 0, whenever there's a negative infinity in the alignment scores, we end up with a 0 in the softmax, in the scores after the softmax, which means that output Y will not depend on the value vector computed at that index. So this is a mechanism to let us control which inputs are allowed to interact with each other in the process of the computation. And we might want to do this now for language modeling, right? Because now we've generalized this operator to the point where we don't need an RNN at all. We can just use this for the same problem that we used to use an RNN for. So now we can use it to process sequence of words, like attention is very, and then output is very cool. So then in this case, we're doing this same language modeling task that we saw last lecture with RNNs, but we can now just do it natively with this self-attention block. But in this case, we want to make the first output is only depend on the first word, the second output very, only allowed to depend on the first two words. We don't want to let the network look ahead in the sequence and cheat. So here is where we would use masking. Another thing that we'll sometimes do with self-attention is called multi-headed self-attention, where you run n copies, like h separate independent copies of self-attention in parallel. Why do you want to do this? Because it's more computation, it's more flops, it's more parameters. Deep learning, we always want more and bigger. And this is another way that you can make this network, this layer more and bigger and more powerful. So what we're going to do is take our inputs X, route them to H independent copies of separate self-attention layers. Those will each produce their own outputs Y, which will then stack up along the output, and then and then have another linear projection at the output to kind of fuse the output data from each of the independent self-attention layers. And now in this case, this is called multi-headed self-attention, and this is basically the format that we always see in practice. So this is like, whenever you see self-attention used these days, it's almost always this multi-headed self-attention version. And in practice, it turns out that you can compute this all with matrix multiplies as well. So you don't have to like run a for loop. You can compute each of these H copies of self-attention all in parallel if you're clever and use batched matrix multiplies all in the right places. So in fact, this whole self-attention operator seems like a lot of stuff going on, but it's really basically just 4 matrix multiplies. We have one matrix multiply where we take our inputs and project them to queries, keys, and values. We have another matrix multiply where we compute QK similarity. For each Q, we compute the similarity against all the Ks, and that's one big batched matrix multiply now in the multi-headed case. We have another one called V weighting, where we want to take linear combinations of all the values weighted by the softmax entries, and that can be done in another big batched matrix multiply. And then finally, we have an output projection to mix information across our different heads of our self-attention. So even though there's a lot of equations, there's a lot of vectors flying around, this whole self-attention operator is basically just 4 big batched matrix multiplies. And that's great because matrix multiplies are a really scalable, powerful primitive that we can distribute, we can optimize, and we can make this thing highly parallel, highly scalable, highly efficient. Yeah, the question is that the X1, X2, X3, they're exactly the same. But we're just gonna like have basically separate copies of the self-attention layer. They will all be random. They all have different weights critically, and those weights will be initialized randomly different at initialization. So they will end up learning to process them in slightly different ways. So this is just a way to give extra capacity to the layer. No, the only thing different between the different heads is the weights. So the architecture is exactly the same, the computation is exactly the same, but they'll have different weights, and those weights will be initialized to different things at initialization. But other than that, it's all exactly the same. Okay, there's some stuff there that we can skip, but now basically we've gotten to one really interesting place where we have basically 3 different ways to process sequences that we've seen in this class. The first is recurrent neural networks. We saw that recurrent neural networks basically operate on 1D ordered sequences. And they're really cool, they're really powerful, people like them for a long time, but they're fundamentally not very parallelizable because of this concurrent structure where each hidden state depends on the previous hidden state. Then they're just a fundamentally sequential algorithm. There's no way to parallelize this across the sequence. And that makes them very difficult to scale, very difficult to make very big. Another primitive that we've seen is convolution. And convolution basically operates on multi-dimensional grids. We've seen it in two-dimensional grids in the case of images. You can also run them on 1D grids, 3D grids, 4D grids. And convolution basically is something that mixes information locally in n-dimensional grids. This is great. It's very parallelizable because by this notion of sliding a kernel around a grid, each position that we might want to place the kernel can in principle be computed in parallel. So this is a very parallelizable primitive. But it has a hard time building up large receptive fields. If we want to summarize an entire very long input sequence or an entire very large image with convolution, we either need to have very large convolutional kernels or stack up many, many, many convolutional layers. So that still introduces some fundamental sequentiality in the way that we need to process large pieces of data. And now self-attention basically is a separate kind of primitive that operates on sets of vectors. It sort of naturally generalizes to long sequences. There are no bottlenecks in the way that there are in recurrent neural networks. There's also no necessity of stacking up many, many layers of them to let all the vectors look at each other. In one layer of self-attention, every vector looks at every other vector. So with just one layer, you can summarize, you can do a lot of computation. And it's also highly parallelizable. As we saw, the whole operation is just 4 big matrix multiplies. And matrix multiplies are a great primitive that we can distribute, we can run on GPUs, we can run in very scalable distributed ways. The only downside of attention is that it's expensive. It ends up having n squared compute for a sequence of length n, and n squared or later on memory for a sequence of length n. And if your n ends up being like 100,000, million, 10 million, n squared becomes very expensive, but you can solve that by buying more GPUs. So that's basically the solution that people have come up with here. So basically, attention has become this super awesome primitive that is super powerful for processing very arbitrary pieces of data. And you might be wondering which of these you should use. Attention is all you need. It turns out that of the 3, you can get a long way using only attention. Yeah, the question is parallelizable. What's the advantage of that? The advantage of that is that in the history of computing, it gets hard to make processors faster. Right? We've sort of run up against this limit as a fundamental limit in hardware, that it's become very difficult to make individual processes faster. But what we can do very easily is get a lot of processors, right? So the way that we've able to marshal more computation over the last 2 decades is finding algorithms that do not require running on one really fast processor. But instead, if we can have an algorithm that can make use of 10 processors, or 100 processors, or 1,000 processors, or 1,000,000 processors, I want to blanket the entire Stanford campus with processors and have all of them working together in concert to process this big thing. If we can find algorithms that do that, that's how we can scale up and get really big, powerful computations. So the benefit of parallelizability is that if you have algorithms that can trivially make use of more and more and more processors in parallel, then we can scale up those algorithms without having to wait for our individual processors to become faster, which they may never will. Yeah, is there a trade-off with the n squared? I think the n squared is actually a good thing. So it seems bad. You're taught in computer science that higher parameters inside that n, that those is bad. But in the case of neural networks, for compute, it could actually be a good thing. Because more compute means the network is doing more computation. It has more ability to think, more ability to process. So actually, the more compute the network does on the input sequence, actually, maybe the better answer it could arrive to. So it means that, it's more expensive, but that's not necessarily a bad thing. So basically, the transformer is now a neural network architecture that puts self-attention at the core of everything. So our input is going to be a set of vectors x. Then we're going to run all those vectors through self-attention, which is, as we just said, this amazing primitive that lets all the vectors talk to each other. After that, we'll wrap that self-attention in a residual connection for all the same reasons that we wanted to use residual connections in ResNets just a couple lectures ago. Then we will take the output of that residual connection, pass it through a layer normalization, because as we saw in ResNets and in CNNs, adding normalization inside your architectures makes them train more stably. But then now there's something interesting, because the self-attention, basically what it does is compares all the vectors with each other. And that's a very useful primitive. That's a very powerful thing to do. But we also want to give this network the ability to perform processing on vectors independently, one by one. So then there's a second primitive inside the transformer, which is the multi-layer perceptron, MLP, or also called FFN. But basically this is a little 2-layer neural network that operates that is run independently on each one of our vectors inside. So then this kind of works in concert with the self-attention, whereas self-attention lets all the vectors talk to each other and compare with each other, and the FFN or MLP lets us perform computation on each vector independently. We'll also wrap the MLP in a residual connection, put a layer normalization, and put a box around the whole thing and call it a neural network block. So this is our transformer block, and a transformer is just a sequence of transformer blocks. And these things have gotten much, much bigger over time. The architectures haven't changed too much since 2017 when this was introduced. The original transformer was something like 12 blocks, 200 million parameters, and now people are training transformers with hundreds of blocks and trillions of parameters. So this same architecture has scaled across many orders of magnitude in compute and size and parameters over the past 8 years. They can be used both for language modeling, as we've sort of already seen. They also can be used for images. And here the application is fairly straightforward. Given an image, we basically divide the image up into patches, project each of those patches separately into a vector. Those vectors then get passed as inputs to our transformer, and then the output gives us one output from the transformer for every patch in the input. Now, if you want to do something like a classification score, do a classification problem, then you do a pooling operation on all the vectors coming out of the transformer and have a linear layer that predicts your class scores. So that's then this same architecture of a transformer can be applied both to a language and to images and to a lot of other things as well. I mentioned there have been a couple minor tweaks to transformers since they were first introduced, but we're running out of time, so I'll just leave those as extra reading. So then kind of the summary of where we get to at the end of this lecture is basically two things that I promised at the beginning. One is that we introduced attention, which is this new primitive that lets us operate on sets of vectors. It's highly parallelizable. It's basically just a couple matrix multiplies. So it's highly scalable, highly parallelizable, highly flexible. It can be applied in a lot of different situations. And the transformer, which is now a neural network architecture that uses self-attention as its main computational primitive. And the transformer is basically the neural network architecture that every application in deep learning is using these days. So that's super powerful, super interesting, super exciting. The transformers have been with us for like 8 years now, and I don't see them really dying anytime soon. So that's pretty exciting. So that's basically it for today's lecture. And then next time we'll come back and talk about some new tasks, detection, segmentation, visualization, and see how we can use these architectures to do new cool things.